All right. Well, good afternoon and good morning to those who are on the Pacific Coast. We're so happy to have you. Welcome to the Carbon Solutions webinar series, where we like to highlight work we're doing within our company and with our partners. I'm Jacqueline, and I'm absolutely delighted to have each and every one of you joining us today. Today, we have Jonathan and BJ who will be presenting on NECTAR. NECTAR is a data-driven approach that can inform where DAC could be deployed to meet energy transition and climate targets. So please note that this meeting is being recorded, and you'll be able to view this presentation along with our previously recorded webinars on our YouTube channel. We would like this to be more than a one-way conversation, so please, we encourage you to share your thoughts, questions, experiences in the chat. And then we've also dedicated time for a Q&A session after the presentation, but feel free to drop your questions throughout the session as they come up in your mind. Thank you again for being here, and with that, I'll pass it to Jonathan and BJ. Thanks.
Thanks, Jacqueline. And thank you all for coming to join us today or watching this recording on YouTube. Today, BJ and I will both be talking about our one of our new tools that we're developing called NECTAR, which can help figure out where the best locations are to site direct air capture, or DAC. I know that we have a lot of different folks from different backgrounds on the call today. So before we get to NECTAR, I'm going to give some high-level background kind of on carbon dioxide removal and DAC in general before we get to NECTAR. So one thing I like to say is, carbon dioxide removal, or CDR, are technologies or approaches for removing CO2 from the atmosphere. And I like to say that CDR puts the net in net zero. And like this slide says, if you didn't have CDR, it would just be a zero emission or an absolute emission target. And so I know that the term net zero gets thrown around a lot, but when you hear that term, you should think CDR. And there's really three different reasons why CDR might be needed in the net zero framework. So the first is just to accelerate the pace to reaching net zero. And so again, the more CDR that we deploy, holding everything else constant, the faster we're going to get to net zero. And then the second reason could be offsetting emissions from hard to decarbonize sectors or processes. And so this is, after we hit net zero, there is certain technologies or sectors of the economy that are really expensive to decarbonize. And so it's possible that we may want to continue allowing those processes to emit CO2. And those are sometimes referred to as residual emissions. And then we can remove those small amounts of residual emissions with CDR. And then the last kind of role that CDR might play is to remove historic emissions so we can still achieve or hit our warming targets. And so this is once we, if we take too long to hit net zero, we may have already emitted more CO2 than we're allowed to from a carbon budget perspective. In which case we'll need to deploy CDR to remove those historic emissions. And I know that this third one is a little bit complicated to think about. So I've got one slide here to kind of convey this more. So the IPCC, in their most recent mitigation report, they ran thousands of different scenarios of many different models. And they found that across all these scenarios, one of their conclusions was that global greenhouse gas emissions have to peak before 2025 if we want to limit warming to 1.5 or 2 degrees C. And to put this in context here, this is the Keeling curves. This is data on the CO2 concentration in the atmosphere, and this is time. And so you can see here that we're just exponentially increasing the amount of CO2 and greenhouse gases that we're emitting to the atmosphere. And so if you think about that in the context of this finding from the IPCC, before 2025 means 2024, and that means this year. It's not looking like we're about to plateau these emissions if you just think about where this curve is going. And so if we want to maintain a 1.5 or 2 degrees C world, we're going to have to deploy more CDR, carbon dioxide removal, moving forward. And the more that we emit greenhouse gases beyond this year, the more CDR we need to offset those. And so overall, CDR is likely going to be a really big deal. And direct air capture, or DAC, is one approach to CDR. And I really like this quote from the Lawrence Livermore report a few years ago. Just really simple. Direct air capture is a machine that's built for the purpose of removing CO2 from the atmosphere. And there's many different DAC technology developers out there that are developing different approaches for these machines, but I have a couple of pictures here that I pulled off of Google to give you a sense of what some of these may look like. These are machines that are currently being built and running right now, and to give you a sense of scale in comparison to a human, what they look like. And so when we think about these three different roles that CDR may play and DAC may play, the next question you may be wondering is, how much DAC is needed in the USA in 2050? And the short answer to this is 0 to hundreds of millions of tons per year. And that's a very big range. And it's a big range because, we don't know how much CO2 we're going to be emitting in the future, and what other technologies are available in addition to DAC that can provide CDR. But the longer answer, if you look at the energy transition studies, and I've pulled out like three big ones here: the LCRI Net Zero America, which was done by EPRI and GTI, as well as the IPCC or the Princeton Net Zero study. They all ran multiple scenarios of different models, and the maximum deployments across those scenarios are shown here. So on the low end is about 100 million tons in 2050, and the Princeton Net Zero is about 700 million, almost 1 billion tons by 2050. And I want you to all to remember these three capacity numbers because they'll come up again in the future slides. But just putting that in context here, the DOE DAC Hubs program is contributing funding towards 4 million tons a year for 4 different DAC hubs. And so if you think about that in context of this, you can see that that's really just going to get this industry started, and we will probably have a lot more deployment to do in the coming decades. And that brings in kind of this question next, which is a question that we've been thinking about at Carbon Solutions a lot, which is where should this DAC, where should these machines be deployed? Where should they be built? And this is a really interesting question. And the reason it's so interesting is that it really depends on a variety of factors. One of which is what we'll probably be focusing a lot on today, is how the performance change due to weather. And this can be both thinking about the magnitude and the variability of weather. And so magnitude, you can think of that as like, how hot is it outside in any given moment? But then of course we all know that the temperature changes outside through the seasons and through the years. And these DAC machines, they're very expensive, and they're going to be, once they're built, they're going to be run for many years. And so knowing how the weather can change over these long time periods is really important. And to make this even more complicated, because weather is already complicated, one thing that we've learned over the past year at Carbon Solutions is that many DAC systems can perform much different than one another in different weather conditions. And so this is some kind of teaser slides here, some results that we'll talk about more later. But this is based off a paper that we just published, shown here, on liquid solvent, sometimes called high temperature DAC. And this is a snapshot of how a 1 megaton system may perform over different combinations of air temperature and relative humidity combinations. And this particular system prefers it to be very hot and humid. And so that's why the Gulf Coast kind of lights up as being the most CO2 that we can sequester and remove, versus over here in the West, where it's less hot and humid. If you contrast this to a different solid sorbent or low temperature DAC system, this is from a different conference paper that we also recently published. Here, this map is just showing how much thermal energy is needed to remove 1 ton of CO2, and as a function of air temperature and humidity. And so here, actually, lower numbers are better because that means you need less energy to capture a ton of CO2. And you can see here that actually the the western U.S. Is more favorable, and that's because this particular system prefers it generally colder and more arid. And so when you think about weather and its implications, that's a really DAC technology specific factor to think about. But across the board, in addition to just weather, there's many other factors that may be considered, and depending on the situation, some of these may be more important than others. But energy is a big one. DAC is very energy intensive. A lot of DAC approaches need both electrical and thermal energy. And so knowing where that's going to come from and how that changes geospatially also factors in where DAC should be deployed. And then, of course, once you capture the CO2, knowing what to do with that and where that goes and potentially transporting that CO2, maybe the locations that are best for CO2 storage are not the same as that are best from an energy or a weather perspective. Also, thinking about energy and environmental justice, and knowing that the energy system has historically disproportionately affected disadvantaged communities, and knowing that we have an opportunity here to think through this and deploy this new energy technology in a way that can maybe rectify some of these past injustices, and knowing that these disadvantaged communities are also not also have a geospatial distribution to them. And then there's, of course, many other considerations: water use, land ownership, and overall, when you think about the scale that we need to get to, again, hundreds of millions of tons in the next few decades, as well as the pace of achieving that scale, and the fact that we potentially need to consider all of these factors within that, you can see that this gets to be a really, really complicated problem really, really fast. And kind of sum this up here, this is a quote from someone that works at a DAC company that I talked to last summer, who said that DAC is harder than rocket science, and I really like that because I think it sums it up pretty nicely, and it also kind of leads me to this. This is the problem that we're trying to solve with NECTAR. And as we were making these slides, BJ and I were trying to think of a way to kind of communicate this, and kind of our cheeky analogy was that DAC kind of takes this from rocket science to routine, NECTAR does. And so, what NECTAR is, it's a data-driven approach to DAC siting, and we're developing routine methods that we can quantify these geospatial trade-offs for all these factors, and make that data and information and put that in the hands of decision makers to help make the best decisions on where they should deploy their technology. And we've been building this tool for a couple of years now through DOE's SBIR program, and we're about halfway through our phase 2 project with them. And so the rest of this presentation, we're gonna present 3 case studies to give you an example of how NECTAR can be used. And so the first is from a non-governmental organization or NGO perspective, and the second is from a CO2 storage developer. And these are both scenarios where Carbon Solutions, we would be using the NECTAR tool ourselves to provide information to these potential clients. And then third is giving you a glimpse into the future of maybe some software as a service offerings that we're developing right now. And this would be potentially giving you the ability to use NECTAR yourself. And so these are all based on these case studies. We tried to make them as realistic as possible, and they're all based on either ongoing work or conversations that we've had with different people. And so I'm going to give the first one, and then I'm going to turn it over to BJ for the second 2. And so again, this first case study here, this is again from the perspective of a non-governmental organization that's doing policy analysis. And they're thinking about DAC and how important it is to deploy DAC to reach our energy transition targets, but also that DAC is very energy intensive, and maybe geothermal heat is a good option for this. And then also thinking from the perspective of, the energy and environmental justice, and thinking about, well, what happens if we think about policies that would require this to be deployed in disadvantaged communities or specifically outside of them. And so this was actually the premise of a conference paper that we published that I previously mentioned at the Stanford Geothermal Workshop recently. And so this is just going to give you a little bit of background at a very high level of that study, because everything that we do at Carbon Solutions is grounded in science. And so if you want more information on this study, you can check out, if you just type this into Google, you can see that study. It's publicly available. But it was we ran some process level models to understand how much geothermal heat may be available from sedimentary basin resources across the U.S. Like is what is shown here. And so, like these spots here in Louisiana and Mississippi, Alabama, are very have a lot of geothermal thermal energy that could be deployed for low temperature or solid sorbent DAC. And then we had the result that I previously mentioned showing how much thermal energy is required by solid sorbent DAC. And then lastly, we got the locations of disadvantaged communities from the energy category of the Climate and Economic Justice Screening Tool. And so I got two slides here to convey the results here. The first is just putting the geothermal heat availability connected with the energy that's demanded by DAC. And you can see that that's what's shown here is that this is the potential capacity that this geothermal heat could enable. And you can see here the higher or the lighter, the yellows, are locations that have more DAC potential deployment as well, and then the purple is lower potential deployment. And you can see here that despite Alabama and Louisiana having favorable geothermal energy, because the weather is generally hotter and humid there, you get different locations like Oklahoma and South Dakota that pop out as being most favorable, and that's because of the importance of weather. And when you add up all of this capacity across the country together, we found that there's almost 5 gigatons of capacity for solid sorbent DAC that can be driven by sedimentary basin geothermal resources. And those 3 capacity targets that I mentioned before from the Princeton Net Zero study, or the IPCC, or the Low Carbon Resource Initiative by EPRI and GTI, are shown here. And so you can see that this 5 gigatons is orders of magnitude more capacity than we may need to reach our energy transition and net zero goals. And also, when you break this out into knowing what percentage of this capacity is co-located within disadvantaged communities or outside disadvantaged communities, that we can also hit our net zero goals on either ends of that extreme spectrum. And so, thinking back to the NGO that's potentially doing policy analysis, one takeaway from this is that you could see that it would be possible to empower disadvantaged communities with the right to veto project development in their communities without placing us in any danger of not meeting our energy transition goals. And so this could potentially be like a win-win situation, both from a community engagement and energy and environmental justice perspective, as well as the energy transition. And so if you want more information about this study, again, you can check it out here. And I will now turn it over to BJ to communicate the second 2 case studies.
All right, thank you, Jonathan, and hello, everyone. So I'm going to take the baton and walk you through the second two case studies. So similar to the first one, this second case study follows the framework of consulting sort of arrangement. What's different is this case study is focused around a client that would be a CO2 storage developer and interested in down selecting among various sites to pursue. So this case study is also going to showcase how NECTAR as a tool can help you understand which sites may be compelling. As with all of these case studies, these are based on ongoing or upcoming work and conversations that we've had. So for case study number 2, there's essentially 2 tasks that are baked in here. The first is a high temperature DAC project. So as Jonathan was mentioning earlier, this system prefers it hot and humid. In this scenario, the project developer would be interested in down selecting among 2 potential sites, one that's more coastal and then one that's a little bit more inland. The second task that we're going to get into is different. So this is a low temperature DAC project, and this system prefers it a little bit cooler and drier. And so for here, there's also the CO2 storage developer is doing CO2 source discovery within a carbon safe application. Next slide. So as with all of our work at Carbon Solutions, this is grounded in science. And so what I'm going to show you next is actually based on work that Jonathan referenced earlier that's now in press in the journal Frontiers in Climate. But let me explain a little bit to you so you can understand better the information you're about to see, what we did. So this is all based on hypothetical, so it's a process level model of a hypothetical 1 megaton per year liquid solvent DAC facility. And so what we did was we essentially created a DAC facility within each location or each grid cell throughout the entire US. So what this means is that there are about 85,000 of these hypothetical facilities spread out across the US. And within each of those locations, because the weather is different, the performance of the facility differs among them. So you look at changes that are due to location. So what you see on the right is a distribution plot reflecting about 20 years worth of weather data. So it's a little bit dense. So I'll kind of explain it to you. So this is a distribution plot on the horizontal axis. As you move from left to right, you go to facilities that are able to that perform better. So they're removing more carbon dioxide in the atmosphere. So all other things being equal, you would want to develop a facility somewhere over toward the right. So that would be a higher performing DAC facility. But you'll notice a bunch of different squiggly lines on here. So the one way to look at this is to consider an individual line represents a year's worth of data, and it represents all 85,000 of these facilities. So the integrated area under the curve for that given line represents the total hypothetical capacity for the United States for that given weather year. So what you'll notice there is that the lines differ quite significantly from year to year. So, you might get some years where it looks like the peak is much lower than other years. All of these differences are due to weather. But what stays constant throughout it is that essentially there's a bimodal nature to the DAC performance throughout the US. And that's something that's fairly interesting, and we talk about that in the paper. So if you're interested in that, you can just Google the paper that's down there below. So next slide. So now on to the task, the analysis results from the first task. And so if we take that data that was on the previous slide and we want to sort of represent that in map form, What we did here was we essentially took an average of all of those 20 years, and so created an annual average and displayed it in map form. And the way to look at this is brighter colors, sort of yellowish, bright green colors, mean greater DAC performance, and the cooler colors, the blues, they represent lower performing locations. And so the first thing that you'll notice is in choosing between these two different locations, one that's in LA that's closer, and again, this is high temperature DAC, so there's a preference towards warmer conditions. The one that's in more coastal is has a higher performance rating than the one that's more inland, closer to the mountains in Burbank. And that difference amounts up to about 110,000 tons of carbon dioxide per year. So what's interesting about that is despite the relatively short distance, we're only talking about several tens of kilometers, there's actually in this region of the country a significant difference in terms of DAC performance. Now, if we kind of want to frame that in terms of dollars and cents, we can assume using section 45Q of the tax code that each ton of carbon dioxide could be worth $180. So therefore, 110,000 tons difference, it would be worth about $20 million per year difference between each of these sites. So to be sure, that's nothing insignificant. Next slide. So there's a second task in this study, and this one is a little different. And so we're considering a single site in this location located in the Midwest. And so for this, actually, Avalon has given us permission to use this slide. And so this is going to illustrate part of this carbon safe project that we're involved with them. So when you do a carbon safe application, you need to have backing from the emitters that are in the area. And so for this, we're going to Concord data. So Concord is a different carbon solutions product that you can use to identify the location of emitters in the area. And so on this map, you'll see the location of interest, well number 2, is centered right there in the middle. And around it, you can see a variety of dots that are color-coded based on the facility type, and that also range in size, which indicates the magnitude of those CO2 emitters. And so using this Concord data is an interesting way to sort of sleuth out who the emitters are in the area. Now, if you're interested in Concord, you can go to last month's webinar, which you can find on our YouTube channel, and it'll show you all about Concord. So additionally, a developer may be, while they're primarily interested in the local emitters in the area, they may also be thinking about things in terms of future preparedness for a DAC facility. So in other words, if we build this, they will come. So if we put a well here, maybe a DAC company in the future will come along and also want to do a project here with this. So for this, we are bringing in, to look at the potential of a DAC facility, we were bringing in data from NECTAR. Next slide. So in addition to who the local emitters are, we also may want to consider, developer may also want to consider what the performance of a facility would be. So as opposed to the previous task where we were looking at time average data, now we're looking at DAC performance through time. And so this animation is stepping us through the weather years. And a little bit different than the previous one. For this one, this is would be a low temperature DAC system, and the cooler colors are indicating are more favorable. They're indicating less energy required to produce each ton of CO2, and the brighter colors, the yellows, are indicating more energy. So a DAC developer would be interested in locations that are showing that much less energy to be required for each ton of CO2 is what you're trying to shoot for. So this is relevant because a project developer might be on the hook for meeting certain targets. And so what we can see here on this map is that weather or interannual weather variability is actually imposing pretty strong controls over the amount of energy required to produce to run DAC. So this shows that utilizing averages alone or climate normals is not really sufficient, especially if you want to know about risk. And so right away, in terms of risk, we can, from this alone, we can quantify a temporally varying range of about 2.5 to 4 megawatt hours of energy required to remove each ton of CO2, depending on the weather year. So this, again, is a pretty interesting finding. So next slide. So let's shift gears a little bit to a different kind of case study to sort of demonstrate some of the advantages and capabilities of NECTAR. So for this one, this is a little bit different. This would be a software as a solution approach. And we're going to take the framework of a DAC developer that's interested in modeling and optimizing their sort of proprietary design for their DAC facility. So this developer would be more in the design phase and seeking to sort of optimize that design. What I'm about to show is a SaaS solution that should be able to fit seamlessly within any kind of sort of testing framework. So some of the questions of interest that a DAC developer may have are what regions within the country have weather patterns that most closely match our ideal operating conditions for our DAC technology. Alternatively, how well will our DAC system perform under the sort of real world weather conditions that we're likely to experience at this location? So while these questions might seem sort of straightforward, of course, you know, weather data, a lot of it's freely available. You can go out there and access it yourself and plug it in. The reality is when you start to take steps towards doing that at, you know, given hourly data and assuming sort of high resolution, you want to know this on a fairly granular scale. That's going to require about 1.7 billion data points per weather variable per year. So that's a pretty heavy lift. Now, what NECTAR's SaaS offering does is it does this sifting for you in a matter of seconds. Next slide. So if we want to kind of think about how this might work in terms of a process diagram, we can start in the upper left here. So a user, for example, that's seeking weather data might want to input some statistics or metrics that sort of define the weather conditions that they're interested in. Now, while not included here, I'm going to mention that we're expanding this to include in the future metrics that indicate capacity for CO2 storage in the area, as well as metrics for energy and metrics for environmental justice data layers too will be included in this. So the user would input those metrics and pass those to the API over there in the blue box on the right. So hit the API would then talk to our database, and then that would return some results to the user in the green box below. So a list of locations that match those criteria. And then the developer could down select among those locations and say, choose the 5 most representative per region or the 500 most representative locations per region. And those would essentially be returned by the API down below, and out would be produced a time series of all of those weather data, and those could be used by the DAC company in their process level modeling. So essentially, running through that in just a matter of seconds, going from the point of I know the conditions I'm interested in. Now hand me some high resolution weather data that's of interest. Next slide, please. So there's a lot of different weather data to choose from, but let's kind of look at an overall framework of how this SAS offering might work. So basically, there's 3 steps. The user would input some metrics. The metrics would generate some results, including locations and a map, and then an output of the time series would be generated after that. So next. If we want to get a little bit more specific about that, and let's kind of distill this down just to a single variable of interest, let's just consider temperature. In the simple example, the user would input a range, for example, of mean annual temperatures of interest, and then some information about the annual temperature variability of locations that the facility would tolerate. Those would then lead to some results returned by the clustering, and then a map of the locations, and then out comes the final time series. So let's get a little bit more specific even than that, and I'd like to show you an animation of how this API would work. So from our end. So next slide. So this is just an animation loop we're going to look at. So here are some weather metrics that are input. We're going to further select some states that are of interest. So Texas and Arkansas and Louisiana, we're going to down select even further. Say we're only interested in those locations. And then out pops a map of the results. And so we see some clustering results here of the locations that sort of match those criteria. We have also the metrics that define all of the locations within that area. And then from here, we would down select only the locations within those specific area, say the top 5 or the top 500 that match. And then that would result in, we could click and download a CSV file of all of those data. So the point in showing this is that this is, while it's a fairly simple framework, it's very extensible and powerful. And so it can very quickly get you to the data that you're interested in, and could fit in a variety of different workflows. And so there are multiple different ways that NECTAR data can be hosted and can be provided. And so with that, I'm going to hand it back over to Jonathan for some concluding thoughts.
Thanks, BJ. And so again, just to wrap up here, again, deploying DAC there's many different geospatial factors you need to consider, and we're developing NECTAR as an approach to quantify and balance different geospatial trade-offs. And hopefully the 3 case studies that we gave today kind of give you a taste for the type of questions and problems that we can apply this tool for. But I just also wanted to mention that, you know, we're just getting started here at Carbon Solutions on this, and over the next year, we're going to be expanding, like BJ mentioned, with this clustering to think about things like energy, water requirements, CO2 storage, as well as do different analyses about, you know, risk assessments. Maybe once we have all this data together, we can think about where are the best places to put DAC hubs, and then also think about spatial representativeness. And so, like BJ mentioned, this is, you know, billions of data points for very high resolution. Do you need that resolution, or is doing things at a lower resolution? Are there different applications where that's possible? And then, like we mentioned, we got many things coming down as far as user-friendly front ends that you can, you know, change different process level assumptions and get different visualizations of how that changes the results, as well as APIs that like BJ kind of gave you a taste of here. And so if you're at all interested in any of this, you know, definitely shoot me an email. You know, happy to talk. And also too, we are looking for some beta testers later this spring or summer for that initial SAS project that BJ mentioned. So if you want to be a beta tester, you're interested in that, please email me. And with that, I just want to thank DOE for the funding, and also thank all of you for your time and attention today. And I hope you enjoyed the presentation, and I'm happy now, BJ and I are happy now to take any questions that you might have. And sorry, it took me a second. So if you have any questions, just, feel free to put them in the Q&A. We've got one question here. What factors led to the preference for geothermal energy potential powering DAC systems, and how does it compare to other options such as renewables or nuclear energy? So that's a really good question. Why did we pick geothermal for that case study? My background as a scientist is in the geothermal world, so that was close to me. But like I mentioned, we're very interested in expanding to other low carbon energy sources, which we'll be doing over the coming year. Right. I'm not seeing any other questions. So if there are no more questions, if there is a question, please put it in the queue. Oh, looks like there are some coming in the chat. Sorry, there's two different. So we had a question: have you made contact with Heirloom to understand their processes? And so Heirloom is a direct air capture company, so we have been in contact with many DAC companies. I can't really speak to publicly which ones we have or have not talked to, but if you're talking on behalf of Heirloom right now, I'm very happy to set up a call and we can talk more in the future. Another question: could you please talk a little about considerations? This is one for you, BJ. Could you please talk a little about considerations of future climate change's effect on weather and the associated scenario uncertainty that we're developing in the tool?
Sure. Yeah. And so this is something we have. I guess the first thing is to dig in a little bit to the weather data sets. We have considered a variety and done a comparative analysis of a number of weather data sets. And so the results that you are seeing on that one is based on reanalysis weather data set and data, so historical. And the reason for that is that these data are effectively tuned to observations to as closely match the observations as possible, which is very key. So it is a historical kind of backward-looking way of considering weather as opposed to a future-looking way. Now, when you get into sort of future scenarios, which is something we're going to expand into in the future, we've looked at those data sets, but they're different. And the first and most striking difference is the resolution. So the spatial resolution of those data are very different. And so for right now, I think the focus is on very granular data that's very closely matched to observations, what has historically occurred. But we will be integrating future climate data carefully, I think, in the future. Yeah.
We got another question saying that Nevada is the second largest state with untapped potential for geothermal, and wondering if our study explored options there because the map did not have any info for Nevada. So yeah, so the map that we were looking at was very specific to sedimentary basin geothermal resources, but there are hydrothermal and EGS geothermal resources, and those of course are in Nevada. We just weren't looking at those specifically for that study, but we are actually working with a couple partners to think through EGS resources and how that potential may enable DAC in states like Nevada. So stay tuned for that. We'll probably have some papers coming out on that question in the future. Great. Well, I don't see any more questions streaming in. So if you do have a question or you're watching this on YouTube and you want to talk, definitely please shoot us an email. We're happy to talk. I want to thank you all again for attending the webinar, and I hope you all have a great rest of your day. Thank you.